Hello and welcome back to Real Analysis. And as always, many thanks to all the nice people that support this channel on Steady or PayPal. In today's part 18, we will talk about the Leibniz Criterion. In short, it's a theorem that gives us a sufficient condition for a series to be convergent. As a good introduction for this, let's recall a series you already know, the harmonic series. It's the sequence of partial sums where we sum over 1 over k. A nice visualization for this would be to look at rectangles. Here all the rectangles should have width 1 and the height should be given by 1 over k. This means that the area of the rectangles are given by our numbers we want to sum up. Of course, here the area of one rectangle gets smaller and smaller when we go to the right. However, we have already shown that the whole infinite sum, the whole area, is infinity. In other words, the harmonic series is not convergent but divergent to infinity. Therefore, having a sequence inside a sum that goes to 0 is not sufficient for convergence of the series. However, we know from the last video it is necessary. Okay, now the Leibniz criterion will fix this missing sufficient condition. For this, we also can use the same visualization. Let's again look at the rectangles from before. However, now we want to alternate the signs of the areas. Hence, the first area is positive, the second is negative, the third is positive again, and so on. Therefore, we don't look at the harmonic series here, but rather at a sequence of partial sums where we have -1 to the power k plus 1 in front. So we have the same sequence involved, but now with alternating signs. And now the Leibniz criterion tells us this is indeed enough to make the whole series convergent. Therefore, please remember, adding, subtracting, and so on gives us a different behavior than just adding. Okay, now we are ready to formulate the general Leibniz criterion. For obvious reason, this is also known as the alternating series test. Of course, there are also other names, some people just call it Leibniz's test. Okay, for the formulation, let's take a sequence of real numbers called ak. Now we already know if we want a convergent series, we need this sequence to be convergent with limit 0. However, now we also put in that ak is monotonically decreasing. So please keep in mind, this is exactly what we have for 1 over k. And now the conclusion is that the alternating series here is convergent. This means whenever you see you have alternating signs, you can always check if the Leibniz criterion is applicable. You just ignore the signs and look if the remaining part defines a sequence with limit 0 and is monotonically decreasing. Okay, now I guess you are interested in the proof of this statement. Indeed, this is not so hard. We just define the partial sums as always, and then we will look at suitable subsequences. So here you see the formulation is a little bit different than before, because here we shifted the index by 1. Which is of course no problem at all, but the picture changes a little bit because the first member here gets a minus sign. Hence now you see here the correct visualization for our case. Now the first thing you should note here is that all the AKs are non-negative because the limit is 0 and the sequence is monotonically decreasing. Therefore, this picture is indeed correct. Maybe the sizes of the rectangles are different, but we have that they don't get larger when we go to the right, and we have the alternating sign. Now the first idea, the first subsequence, is that we only consider even ends here. Because then you see here, the negative part dominates. So let's take a natural number L, then this index is even. And then we subtract the predecessor given by an even number as well. Therefore, in the picture, what remains are just 2 rectangles, maybe here. And then we know by assumption that the right area here can't be bigger than the left area here, of course, measured with the absolute value. On the other hand, in the formula, this looks like this. With the same reasoning, when we subtract the 2 partial sums, only 2 terms remain. And only the odd number gets the minus sign. Now, since the sequence is monotonically decreasing, this is less or equal than 0. That's what I said, the negative part here dominates. Okay, maybe not so surprising, we can do the same for odd indices. This works completely the same, but only shifted by 1 index, which means now the positive part dominates. Of course, we see that in the formula as well, these two members remain and the odd index gets the minus sign. Therefore, this is again by the monotonicity greater or equal than 0. Hence, the odd indices give us a monotonically increasing subsequence. And on the other hand, we have a monotonically decreasing subsequence for the even indices. Okay, then in the next step, let's compare both subsequences. In other words, what is the difference between the members with indices 2l plus 1 and 2l? Also, this is easy to calculate, it's simply minus a with index 2l plus 1, which is less or equal than 0. Hence, we get this inequality when we want to compare both subsequences. And now we can put in that we know that this sequence is monotonically decreasing and this sequence is monotonically increasing. Therefore, for all natural numbers L, we have that S2L is less or equal than S2. And the same on the left hand side with S3. So from this we conclude that both subsequences are bounded. And now you might already recognize one important theorem we had for sequences. We simply called it the monotone convergence criterion. Here in our case we have a sequence given by the even indices, which is monotonically decreasing and also bounded from below. Hence we know it's a convergent sequence. On the other hand, we have a sequence which is monotonically increasing and also bounded. So it's also convergent. We can even show that the limit of both sequences is the same because we can look at the difference again. We already know it's simply given by a sequence member A. Therefore, when L goes to infinity, this sequence goes to 0. So here we put in our assumption about the limit of the sequence AK. Okay, so there's only one limit and we can call it S. So at this point, please recall that we wanted to show that the sequence Sn is convergent. Here we just considered two subsequences. However, both subsequences together hit all the sequence members of Sn. Therefore, we can conclude that the limit of Sn is also given by S. If you have never seen this step here, then it's a good exercise for you to show it. Nevertheless, for us the result here is important. The sequence of partial sums Sn is convergent. And this closes our proof. So we have proven the Leibniz criterion and now you are allowed to use it whenever you can. Therefore, let's close the video with one last example. Let's simply consider a series that has -1 to the power k over the square root of k. So here we have everything we need for the Leibniz criterion. We have alternating signs and a sequence which is monotonically decreasing and is convergent to 0. Therefore we know this whole series here is convergent. We cannot immediately calculate the limit, but we know the limit is a real number. Okay, so that's how you apply the Leibniz criterion. Okay, then in the next video we will talk about other criteria as well. Therefore, I hope I see you there and have a nice day. Bye!